Okay, folks, let me get the sign-in sheet. I've got it. Let's see. And get it passing around. So what we're going to do today is we're going to pick up with our discussion about molarity. And we're first going to calculate the molarity. Once we've learned how to calculate the molarity, then we're going to use molarity as a conversion factor. So that is the plan for today. And then on Wednesday, we will continue using molarity as a conversion factor, and then finally get into using molarity in dilutions. So at the end of Monday's class, I introduced this formula where molarity is moles of solute over liters of solution. Basically, to calculate molarity, you've got to be able to get moles solute and liters of solution and then combine them in the formula in order to get the actual molarity. So let's just start out very straightforward and simple. 1.0 moles of potassium fluoride is dissolved to make 0.10 liters of solution. What is the molarity of the solution? Okay, so the first thing I need is mole solute. Well, I just happen to be given moles of solute in the equation. So my molarity is going to equal 1.0 moles Kf over. Now, the next thing I need is liters of solution. And I was given liters of solution. So that would be that 1 mole of Kf is placed over 0.10 liters of solution. And when we calculate that, we should get 10 if I'm not mistaken. Yes, you get 10 molar Kf solution. So most of the time, I'm not going to write out the word molarity. I'm simply going to use the capital M. That is, again, mole solute over liters of solution. Let's look at another example. What is the molarity of a solution that contains 1.0 grams Kf dissolved in enough water to make 0.10 liters of solution? The first thing I need to find is my moles of solute. Well, in this one, I was not given moles of solute, but I was given grams of Kf. And to get from grams to moles, we would use the molar mass. So if we have 1.0 grams of Kf, we're going to need the molar mass of Kf in order to convert that into moles of Kf. Potassium has a mass of 39.10, and fluorine has a mass of 19. So it has a mass of 58.10 grams of KF is equal to 1 mole of KF. So 1 divided by 58.1 is going to be 0.0172 moles of KF. And now I have that numerator I needed. The next thing I need is I need that liters of solution, which in this case, they did give me liters of solution. So I can use this equation now. The molarity is going to equal 0.0172 moles of KF divided by 0.10 liters of solution. And that gives us a molarity of 0.17 molar KF. So basically, folks, what I'm doing is I am finding the two components needed to perform this calculation. So let's look at another example. What is the molarity of a solution where 952 grams of ammonium carbonate is dissolved in enough water to make 1,750 milliliters of solution. First thing, I need mole solute. Again, I was not given moles of solute. Instead, I was given the grams of my solute. And I can use grams and the molar mass to get to my moles of solute. So let's see, we have 2 nitrogens times 14.01. We have 8 hydrogens times 1.008. We have 1 carbon times 12.01. And we have 3 oxygens times 16.00. So that's 28.02. 8.064, 12.01, and 48. So that's 96.094. That's grams of ammonium carbonate is equal to 1 mole of ammonium carbonate. So I can take my 952 grams of ammonium carbonate and convert that into moles using that molar mass. And you get a value of 9.907 moles of ammonium carbonate. So that is what I need for that numerator. Now for the denominator. I need liters of solution. I was not given the liters of solution though, but I was given milliliters of solution. So I'm going to need to take that 1750 milliliters and convert that into liters. 1 times 10 to the minus 3 liters is equal to 1 milliliter. Or in other words, it's 1.750 liters of solution, which gives me the denominator that I needed. So our molarity is going to be equal to 9.907 moles of the ammonium carbonate divided by 1.750 liters of solution, or in other words, we're looking at 5.66 molar ammonium carbonate. Yes. Okay, I don't round to significant digits until the very, very end. So that's why I rounded to 3 significant digits when I got to the 5.66 molar. But the 9.907, I just carried extra digits so that when I did the math, I wouldn't have a rounding error. Other questions? Let me give you one to do. What is the molarity of a solution made by dissolving 9.82 grams PbNO3 in enough water to make 465 milliliters of solution? Red is number 82 if you're looking. Okay, so in this problem, you would change the 9.82 grams of lead four nitrate into moles of lead four nitrate using lead four nitrate's molar mass. And taking that 9.82 and dividing it by the 455.24 to get 0.02157 moles of lead four nitrate. Then you would have taken the 465 milliliters and converted that into liters using your metric conversion to get 0.465 liters of solution. And then ultimately to get the molarity, you would have taken the 0.02157 moles of lead four nitrate and divided it by the 0.465 liters of solution. And you get out 0.0465 molar lead four nitrate. Any questions? So now what we're going to do is we're going to use molarity as a conversion factor. And the key I can tell you to being able to do this successfully is when using molarity as a conversion factor, rewrite the molarity into its subunits. The value for the molarity goes with the moles. And it is over 1 liter. So I want to illustrate what I'm getting at. If I have a 0.589 molar NaCl solution, I take the couple of seconds it requires to rewrite this to be 0.589 moles of NaCl over 1 liter of solution. Or let's say I have a 0.0925 molar C6H12O6 solution. Then I rewrite it as 0.0925 moles of C6H12O6 over 1 liter of solution. By doing that, you can see that that capital M really stands for two different units. It's moles over liters. And that is the most common error I see with most of my students throughout the years, is when they see that capital M, they think of that capital M as a unit. And that capital M is a unit, but that capital M is really comprised of two subunits. And rewriting that capital M to show the two subunits will actually help when performing conversions. Now, when performing a conversion, as you noticed, I've always taken whatever I am working with. And in my first next conversion factor, that unit is disappearing. I've taken whatever I'm working with, and then the next unit, it's in the denominator so that it cancels out. And taking that unit, whatever's in the denominator cancels out. With molarity, molarity can be flipped. The entire thing can be flipped depending upon what you want to cancel out. So molarity is a really neat unit that can be flipped depending upon whether you want the amount of material or whether you're wanting the volume of the material. So let's just look at some examples. How many moles of NaCl are contained in 0.0100 liters of 0.589 molar NaCl? First things first, I'm going to identify what I've been given. I have been told I have 0.0100 liters. That means I have 0.0100 liters of solution. And I have been told that I have a solution that is 0.589 molar in concentration. So 0.589 molar in NaCl. Now again, that molarity actually means moles of NaCl divided by liters of solution. Now this next statement is important. When I am performing a calculation, if at all possible, I start with a piece of information that has only one unit. When I am performing a calculation, I start with the piece of information that has only one unit associated with it. So in this particular case, I am going to be converting that liters of solution into moles of NaCl, because the liters of solution had only one unit associated with it, whereas that molarity had two, which is obvious if you rewrite it into its subunits. Now, what you will notice is that you have volume of solution and you have moles of solute. That is telling you that you are going to need the molarity. The molarity converts between mole solute and volume of solution. So with this, we're going to start with what we were given, which is 0.0100 liters of solution, and we are going to use the molarity. I want to get rid of liters of solution. So from this molarity, the liters of solution will go into the denominator.
with the moles in the numerator. You place the liters in the denominator so that the unit and the substance will cancel out. And you come up with 0.00589 moles of NaCl. Let's look at another example. What volume in liters of 0.589 molar NaCl would contain 2.00 moles of NaCl. Again, I'm identifying what I've been given. I have been given a molarity here. 0.589 molar. So .589 molar NaCl, which I am going to immediately rewrite to be 0.589 moles of NaCl per 1 liter of solution. The second thing I would notice is I was given 2.00 moles of NaCl. Now I need to figure out which of these pieces of information I'm going to start my problem with. Do I start it with the 2.00 moles of NaCl, or do I start it with the 0.589 molar NaCl? Again, if you have a choice, always start the calculation with a number that has only 1 unit. If you have a choice, always start the calculation with a number that has only 1 unit. So I am going to start with the 2 moles of NaCl, and I am going to be converting that into liters of solution. Again, I notice that I have moles and I have liters. That means my molarity is going to be the conversion factor. So beginning this calculation, 2 moles of NaCl. Well, I need moles of NaCl to be in the denominator if they're going to cancel out. And the only way to achieve that is if I flip this molarity. So I'm going to put the 0.589 in the denominator and the 1 liter of solution in the numerator. It is placed in that order so that the moles of NaCl will cancel out, leaving liters of solution. And when you calculate this out, you get 1.178 liters, or because if you're doing it in significant digits, it would be 1.18 liters of solution. Let's look at another example. How many grams of glucose, which is C6H12O6, is in 237 milliliters of solution of, is in 237 milliliters of a 0.0925 molar C6H12O6 solution. Yes. Two divided by 0.589. Oh, what in the heck did I do? Oh, I see what I did. I'm sorry, that came out to be 3.40 liters of solution. If you keyed it in, it's 3.40 liters of solution. Everything else is correct. It's just the number. I accidentally hit times instead of divide. Which reminds me, I think I've said this before. On the exam, show your work. If you set everything up correctly and you miscalculate, it's usually only 1 or 2 points off out of like 10. So, but if I don't see any work, you would miss all 10. So show your work. It's not fun, but it is necessary if you want partial credit. Okay, so let's look at this one in the last 7 minutes. What have I been given? I have been given 237 milliliters of solution. What have I been asked to solve, or what else have I been given? I have been given a molarity that is 0.0925 molar C6H12O6, which I'm immediately going to rewrite to 0.0925 moles of C6H12O6 divided by 1 liter of solution. And I'm like, which one of these am I going to start with? Again, start with a value that has only 1 unit associated with it. So I'm going to be converting that 237 milliliters of solution into grams of glucose. Now, to convert from solution into an amount, I only have one conversion factor here. To convert from solution to an amount, I've got to go through the molarity. But in order to use this molarity, I need my volume not to be in milliliters. I'm going to need it in liters. So my first task is going to be to take that 237 milliliters of solution, and it is going to be to convert that into liters of solution, with the fact that 1 times 10 to the minus 3 liters of solution will equal 1 milliliter of solution. The milliliter portion had to be placed in the denominator so that the unit and the substance could be canceled out, leaving liters of solution. With liters of solution, you can now use your molarity, and you want to use the molarity in a variation that has liters of solution in the denominator, which this one already does. So I'm just going to rewrite it into liters of, or into the conversion, placing the liters of solution in denominator so that the unit and the substance can cancel. Another thing you should always do in checking your math is make sure you're answering the question that has been posed. I was not asked to get to moles of my glucose. I was asked to get to grams of glucose. How do you convert moles into mass? The molar mass. There is 6 carbons times 12.01. There is 12 hydrogens. Times 1.008. And there are 6 oxygens times 16.00. Which will come out to be 180 something. Which comes out to give you 180.156 grams of C6H12O6 is equal to 1 mole. So I'm going to put that 1 mole in the denominator and put my grams in the numerator. And solve. And when you do so, you get 3.95 grams of C6H12O6. Yes. Questions? Okay, we're going to be doing some more of these conversions on Friday morning or Friday, and then we're going to finish up with the last piece, which is dilutions, which is the easiest part, which is another easy part. Conversions of molarity is probably the hardest part of molarity. And I will see you on Friday.